Hi and welcome to a short video presentation of my Summer of HPC 2016 High Performance Computing project, which goes under the name of Phine quarks and cude gluons. In my project I studied a theory called lattice QCD, which is supposed to mimic the so-called strong force, which is one of the four known fundamental interactions in nature, and is describes the motion and interactions of quarks and gluons, which are thought as to be elementary particles. They are responsible in turn for the existence of protons and neutrons, which form the atom. This theory is modeled by quantum chromodynamics, or short QCD, and although QCD is mathematically very elegant and compact, it is very hard to solve with analytic techniques. But fortunately, there are a lot of numerical methods available with which one can study the theory on a supercomputer. However, the computational demands of lattice QCD are very high, and it's not unusual that one simulation takes up to 1 year of simulation time on a significant part of a supercomputer, and demands for 100 up to 800 teraflops of sustained performance, that is to say 800 trillion floating point operations per second. This is why there is a big need to use new hardware such as graphic cards and Intel Xeon Phi coprocessors early on. Because the simulation time for lattice QCD are so long, it would be nice to have a couple of toy models available. There are very interesting and smaller problems in solid state physics that can be treated with lattice QCD techniques. The similar algorithmic structure for this theories comes because the models naturally rely on lattices or grids, because the solid structure of the material studied and interactions are oftentimes modeled with nearest neighbors only. Usually most of the time in a lattice QCD simulation is spent in solving a sparse system of linear equations, and this is most efficiently done with so-called iterative solvers. They are heavily based on BLAS-like linear algebra routines such as vector times vector multiplications, and the most expensive one is a matrix times vector multiplication. This multiplication, however, is at each site of the lattice described by only a few data elements, and this is known in computer science as a stencil operation. So in my project I was given a code of solid states physics, and we were to optimize this code. Here are a few things we have done. We implemented an allocation-free matrix multiplication in form of the aforementioned stencil operator, and for this we used vector intrinsics to guarantee the full utilization of the SIMD registers of the Xeon Phi card. We also implemented various iterative solvers, for instance a conjugate gradient and the biconjugate gradient solver, and we thought about cache reuse optimization by so-called space-fitting curves. What are the results? We obtained a speedup of the original code of a factor of 10 to 14 depending on the problem size,